Chem. This is really awkward as someone's already watching. Okay, I'll just get this set up. Resources. Okay. Mass spectrometry. Okay. Great. Will it let me wait. Display settings. Swap. Yes. Will it let me draw laser pointer? Oh, that's fun. That's fun. Pen. No. Pen is not allowed. Laser pointer. No. Oh, laser pointer. Okay. Okay, that's something. That's working. There was one more thing. What did I want to do? Sorry if you're watching this and this is awkward. Just give me a second. I need to set this up. Oh, that's what I was gonna do. Wrong team. Year 11. Assessment sheet. Okay. Yes, this is what I wanted. Okay, we'll keep that on there. Will that become used? Right, since I don't know who's here and if anyone's here, I'm just gonna get started and see if it will make a video for me at the end for other people to watch. I don't know. Okay. Here is your task sheet that you've been given, and I'm not going to go through each of these. Most of you by now, hopefully, by the way, you should already have all of this research and put into some sort of document that you can print, or maybe you've written it out. I don't mind. the one thing I wanted to say right up the top is please include a bibliography. If you're finding it hard to make a bibliography, you can go to mybib, or you can go to bibme, one of these two, I don't know. They're both fine. Just put in your references. You don't need a crazy amount of references. Just put in some references and have them, I don't know, APA, Harvard Australia. Oh, I didn't know there was a Harvard Australia. Anyway, APA, Harvard, any of these is fine. As long as there's some structure. I don't just want a list of links and, you know, just doesn't look nice. I'd rather you give me a bibliography of some sort. One sec. Sorry, I don't stream. I don't know how to do this. Okay, let's just do the PowerPoints. In class we did the absorption and emission. This is what we did in class as well. Wait, let me just do the animations. Oh, swap. This is what you can see. Okay. Daily review from today's lesson. We looked at how absorption happens in your energy levels. We've got elements and atoms that usually are at ground state, and when we're answering our questions, we're assuming they're at ground state to start with, and then they're going to absorb some energy and become excited. In this case, with our spectroscopy, they're going to absorb energy in the form of light, and they get excited, and then they transition up to the excited states. Let me get my laser pointer out. Get transitioned up to the excited states from the ground state they are at currently. Once they are up in the excited state, one of these two excited states, that energy is volatile, that electron rather is volatile and wants to return to the ground state, which is the lower energy level, so down here. If it absorbed energy to go up there and now it falls back down, that energy has to go somewhere, and in this case is going to be emitted as a photon of light. Animations. There we go. Emitted as a photon of light. Oh, why is it doing absorption? Okay. Absorbed. Okay, right. Now, atomic absorption spectroscopy. We're going to look at how it's performed and some uses of it. Here's a big machine, your spectroscopy machine, very cool. Okay, what do you use it for? It's an analytical technique that can be used to either quantitative or qualitatively analyze some sort of element, specifically an element. Developed by Sir Alan Walsh. He was Australian from Melbourne in the 1950s. Very cool. Many labs use advanced methods of analysis, but AAS is still really good for Western Australia specifically, because we love our mining. Copper and gold, really good use cases for AAS. Okay, how do we perform AAS? So first, you're going to focus light of a very specific wavelength on atoms of a solution. So you're going to have a solution of some kind with a specific element that you are going to analyze, and you're going to shoot, again, a specific wavelength of light that you know is going to be absorbed by that element. You're going to shoot it at the solution that has been atomized. The measurement of light that is absorbed, so the specific wavelength of light that you are putting through that substance, how much of it is absorbed is called absorbance. And once you find the absorbance, you can then find the concentration of that solution if it was unknown to begin with. To do that, actually, maybe it's the next slide. To do that, you need to first know some initial concentrations and some initial absorbances as well. Although the relationship between absorbance and concentration is logarithmic, we are going to focus on the part of the data that is mostly linear, and hopefully that's okay to, yeah, I don't know what I'm saying. Sorry, let's keep going. For this reason, the analysis is only viable for a range of concentrations. Outside of that working range, it just kind of falls apart. Becomes a little bit more unreliable when you're looking at the data and trying to extrapolate. Okay. Calibration. How do you calibrate it? One sec. I think my stream, I'm sorry about this. I think my stream is not allowing comments for some reason. So if you're trying to communicate with me and trying to say something, I can't hear you. I don't know. If you have sorry about this. If you have a question while I'm talking, I might have to open this on a different window or monitor rather. If you have any comments that you need or questions, put it in the Teams and I'll try and answer. Okay. So messy. Apologies. Yes. Wait. Oh my gosh, my whole computer. Oh my goodness, my whole computer's falling apart. Give me a sec. Right. Swap this, please. Thank you. Okay. Give me my pointer back. Okay. Oh yes, analyzing an unknown. Oh wait, no, calibration first. Calibration first. To get the instrument ready for analysis, a set of solutions is required that only contain the element that you are looking for. For example, if you're trying to figure out an unknown concentration of sodium in a solution, you're going to make sure that it's calibrated, or the machine is calibrated with different concentrations of sodium, and then you can start doing your analysis of the unknown concentration. These are called your calibration solutions. So calibration solutions are going to have a known concentration of a specific element, which is where you get this calibration curve from. This, for example, is for gold, and for gold you'll get a nice linear line with your concentration down the bottom and absorbance values up the left. Okay. The solutions are run on the instrument and their absorbances are measured. The data is plotted on the graph as a basis for the analysis. So you will take, for gold as calibration solutions of gold, you will take a known concentration. So you know for a fact that a certain solution has 10 parts per million of gold. You know that for a fact. Back up here in the table, obviously if it's blank and it doesn't have any gold, you're going to get an absorbance value of 0. Then you have 2 parts per million, 5, 10, and 50. Those numbers are just arbitrary. You don't have to use those exact numbers, but they're there to be used. But you're going to have a few points of known concentration. You know for a fact that this is 50 parts per million. You know for a fact that this is 5 parts and this is 2 parts per million. And then you draw a line in between all of them. And then, oh wait, no, you don't draw a line between them yet. you have to put each of those solutions through the AAS machine, and it will tell you, oh, this solution that you put in has a absorbance value of, let me just go up here and see, 0.26. The machine will spit out that number. You will then put a concentration of 50 parts per million into the machine, and it will tell you, it's the absorbance value is 1.25, and then you take those values, X and Y values, and put them on your graph and draw this line. Very easy. Then you will go on to the next unknown value. Okay, for your unknown value, sorry, I'm a bit lost. To determine the concentration of a sample of an unknown value, it is run on the instrument and its absorbance is measured. So the machine operates on the absorbance values. The machine doesn't know the concentration. Okay, the machine only works on these absorbance values. It does not know anything about the concentration. Only you, as a person running the machine, know the concentration. So it's going to spit out a certain absorbance value for your unknown sample, and then you have to go through and put that value on your graph that you made from the previous slide, your gold calibration curve. Let's say, for example, you take your unknown gold sample. You know there's some gold in the sample, but you don't know how much there is or what concentration of gold there is, and the machine tells you it's 0.4. Then you will take that value, 0.4, on the y-axis, which is your absorbance value, and go horizontal as far as you can intersect with the line that you drew earlier. This is not perfectly intersected here, but you get the point. It's going to intersect with the calibration curve, and then you go straight down. In this case, we are estimating that is going to be a concentration of 15 parts per million when the absorbance level is 0.4 as told to us by the machine. The machine might say it's 0.9, and then you do the same thing and go and intersect on the same calibration curve, go down 35 parts per million. So this job is yours. The machine will only output the value. It is your job to then go and find the value on the curve itself. Okay, let's keep going. I'll do one more slide and then I'll go and check the teams if there's any questions. How does the instrument work? For the instrument to work, it requires, first of all, a flame, which will be your heat source, a method of spraying the sample into the flame, and also a beam of light that is shooting a specific wavelength of light through this sprayed sample that has been inside the flame. You need a way to focus and detect the light. That's where actually, I'll show the diagram later. And a device to show the calibration graph. This is your detector, your computer that will spit out a graph, or not a graph, it will spit out a absorbance value. Okay, 1 second while I look for some, look at the teams. Come on. No questions so far. YouTube is not what? Sorry. Is not receiving enough video to maintain smooth streaming. Viewers will experience buffering. Why are you telling me that? That's none of my business. What? Sorry, give me a sec. Okay. No, I'm not seeing any comments, or questions on the teams. So we'll just keep going. Oh, that's such a shame that I can't see the YouTube comments. Why is it doing that? I'm not gonna stop and start the stream. That's too much of a headache for you guys, not for me. Okay, let's just keep going. Sorry. Pointer. There we go. Okay. Your unknown sample. Okay, so just a reference again. Flame. Your sample is sprayed into a flame. Next to it, there's a light shot through those atoms that have just been burnt up by this flame, and that light is a specific wavelength. And then there's a detector and some computer to spit out results. Okay. A sample solution is drawn through a thin tube and then turned into a fine aerosol using a nebulizer. And this is a real life nebulizer here. You have your sample in this measuring cylinder. This thin tube is going to take up some of that sample and put it into the nebulizer in here. The nebulizer is going to take this liquid state solution and turn it into atoms. Very, very cool. The aerosol spray is then mixed with a combination of air and acetylene gases. I mean, you don't really need to know that, but something to fuel a fire. In the spray chamber. This is a very complex diagram, by the way. If we expect you to do a diagram, you don't have to do a diagram this complex. There's simpler diagrams to use. This diagram here calls the thin tube a capillary. That's the technical term. Thin tube, capillary, same thing. Anyway, the nebulizer is going to make your solution into atoms, similar to what a cologne bottle would do, I guess. Next, a burner. The spray is then forced upwards through to a burner where it is ignited. So these acetyl gases in the spray chamber are there to make sure that your sample does catch on fire and burn. The spray undergoes desolvation, releasing atoms of the sample solution into the flame. Desolvation, again, this is where you're removing the solvent. The solvent most often is water. You're removing the water to make sure it doesn't interfere with the AAS analysis, and the only thing hopefully at this point that is becoming atoms and being burnt up is your sample that you are testing, so gold or sodium or something like that. And then, yep, it's burnt up. Oh, now light source. This here, these tubes are your cathode rays, or your cathode lamps rather. And these cathode lamps are going to emit a cathode, not a cathode ray. They're going to emit a specific wavelength of light that would be suitable for this particular sample. So the light source of the AAS provides a steady, thin beam of light, just like this, just like a laser pointer, but just a little bit thicker, of a wavelength of a specific specific wavelength specific to the element. So this looks like a red light, so you would assume that if you were to burn this element, it would turn a red color. And on Friday we'll do some flame tests and you'll see there should be at least one red sample, or element that turns red anyway. This light source is called the hollow cathode lamp. That's the most technical term. If you see the word light source in reference to AAS, they're referring to this, and it can be synonymous, but I'd rather you just say hollow cathode lamp. The light from this lamp is carefully focused through the flame so that it can be absorbed by the atom released by the spray chamber. So again, spray chamber mixed with some flammable gases, put it through the fire. The fire is burning your sample, and while it's burning the sample, this is when your light or your lamp is emitting a specific light to go through the sample once it has started burning. Now, the light that is transmitted through the flame is measured. The amount of light that goes through the flame is going to be less than the amount of light that we started with. So we start with some amount of light, and once it goes through the flame, you're going to have less light. That difference is because the atoms that are burning up in the flame are absorbing some of the light, hence atomic absorption spectroscopy. Whatever light goes through the flame, the reduced amount of light, is that's the one that is detected and measured, and that is what will give you a certain number for your absorbance value. It's going to tell you how much of the light has been absorbed by the sample that is currently burning in the flame. Okay, I think that's all I can say for that one. Let's keep going. Detection. At the end of the this cathode, this light that is going through the flame. So remember, back here you're going to have a certain amount of light, but some of it is absorbed in the flame, and at the end you're going to have less light than back here. Once the light gets to the monochromator, it makes sure that you are looking at a specific, it's going to sort of refine the wavelengths of light that are going to end up on the detector. Let's just read what this says. The light transmitted through the flame is then focused using a series of mirrors and prisms in this monochromator, and then is sort of refined and thinned out so that you have a nice, easy to detect ray of light. The light is focused into the detector, which converts the light into an electrical signal. Very nice. And then that detector will just tell the computer how much light it's detecting, and then it will tell you how much was absorbed. The detector here is called a photo multiplier tube. If you say detector, I won't be offended. Just say the detector. That's there's only one detector. You don't have to say photo multiplier tube. But if you want to be extra, go ahead. Who's stopping you? I think that's everything. That was everything. Sick. The part that a lot of people asked me questions about was the light source and a little bit of detection. But that's I hope that clears up a little bit of what the machine does. So these 5 steps, is very important that you know them in sequence. So first you have the flame that's burning, then you spray the sample into the flame. There's a specific wavelength of light going through the flame, and some atoms will absorb that light, and then whatever light is remaining that wasn't absorbed will get focused and detected, and then the machine will tell you an absorbance value for that specific sample. That absorbance value then will go on your y-axis. Let's say, for example, again, 0.5. Let's say 0.5 was your absorbance value. You will take that, you'll grab a ruler, make sure it's parallel with these lines, and then go and intersect with your calibration curve that you got, and then go straight down, and you will say it's 28 or something. How do you get that calibration curve? You take some solutions of known concentrations. You know for a fact that it's going to be 10 or 50 or whatever parts per million, or grams per mole. No, that sounds wrong. Grams per liter, moles per liter. And that's how you get your curve. You're going to use some known values to start with. Okay. know this sequence. Okay, let's see again if there's any questions. Give me a second. No questions. Let's go. All right. I might just really quick. If you're still watching, I need you to pay attention to what I'm about to say. I might quickly stop the stream and then change a couple settings so you can send comments if you need to, and then I'll send the link